if you recall, I had right from beginning I have been saying that finite element method was given to the world by structural engineers, So, it is it will be fitting if we also learn the method the way structural engineers normally do, because then some concepts which are still not very clear, because I have taken a mathematical problem, we started from mathematics, because mathematics means it unifies everything, it is a general approach, it covers so many areas. So, we will try to give a small presentation on how simple structural problems are dealt with by FEM. So, if you recall, I had told you that the second order governing differential equation also defines or also governs the behavior of a rod in tension or compression. A rod in tension, not bending, I am just only saying a rod, a simple one dimensional rod in tension or compression is also governed by the same equation, which is d square phi by dx square equal to p or something, of that kind. Now, we will try to first derive that equation. So, if you have a rod under tension, so this is your sigma x. Stress at any point is total force divided by the area of the cross section. So, we are just taking a rod in tension, a rod in tension. Then so, what are the equations that governs this rod, behavior of this rod? If you start from theory of elasticity, simple elasticity, one is equilibrium equation. Equilibrium. So, you must have learned, I think all of you are doing a course on elasticity, or you would have done a course on elasticity. So, one is equilibrium. The rod, every element of this rod must remain in a state of equilibrium under the action of forces. So, what you get is, if it is under uniaxial tension, so you have, let us say, sigma x on this side, but as you take a small element delta x, so this stress will increase by a differential amount sigma dx. And since it is only a one dimensional problem, there is no, it is not a two dimensional or three dimensional. So, sigma dx, so we can also write this is sigma x plus what? Rate of change of x, sigma x with respect to x. So, d sigma, because there is no partial derivative, with respect to x into dx. That is also. So, first is equilibrium. So, equilibrium will give us, or if you recall your elasticity equation, there are three equations of equilibrium in 6 stress components, 3 normal and 3 shearing, 6 components. Now, this is a axial rod in tension, there is only one stress component that is non-zero, all other stress components are 0, sigma y, sigma z, tau ij, all the 3 are 0. So, the only one equation that will be left will be the first equation, So, if you recall that, that will be del sigma x by delta x plus we normally y etcetera is all 0, tau is 0. So, plus body force per unit volume equal to 0. If you take it from there, but that can also be derived from here. See, equilibrium means what? This body is in a state of equilibrium, sum all the forces. This element is in a state of equilibrium, sum all the forces. So, in x direction, of course, sigma x plus you should get the same result by dx delta x. This is the stress. Stress cannot be summed. You have to convert this into a vector force multiplied by the area of cross section. Area of cross section of this rod has area of cross section minus sigma x into A. And in case it has got some self weight, which we call body force. So, body force if you take per unit volume, if you take body force just like this definition is per unit volume. So, per unit volume total body force per unit volume is B x. So, in x direction body force per unit volume, first of all you convert that into force. So, multiply by the so multiply that means B x. So, dimensions must be, see this is per unit volume, if you take this plus let us say there is a body force B x. B x means self weight etcetera per unit volume. So, this multiplied by area into dx, this is the volume. So, this will be the total body force in x direction. So, this can be set equal to 0, and I think both will give you the same result. Now, both should give you the same result. So, this is from physics, from equilibrium, actually drawing the, is it clear or not? Clear. So, this is so this will get cancelled with this area multiplication, and then you get here d sigma x by dx plus Bx multiplied by area into dx is common, and area into dx is nothing but the volume. Whenever two products are 0, product of two quantities 0. So, this volume cannot be 0, since volume is cannot be 0, therefore, so this is a kind of derivation, I mean how we derive the equilibrium equation. So, there is no difference, of course, this partial is, this will turn to ordinary because there is only one. So, this is not partial, this is. So, you have one equilibrium equations, okay. Two, that means which says that forces, I mean every element of this body is in a state of equilibrium. Second one, we relate that particles under the action of stress, particles move and there is a relative motion. So, relative motion causes strain, and these strains are related to the displacements of the particle. So, that one also, for example, here if it is only in this, so there will be only one strain component that will be present, and that is epsilon x, and that will be from your again elasticity, that will be given by, if u is the displacement of any particle. So, that will be given by du by dx. Okay. All other, because here again elasticity you have got 6 equations, 3 normal strain and 3 shearing strain, all others are 0. This is only one dimensional. Third one is material constitutive relation. These are the basic equations of elasticity. Any elastic body must satisfy these basic relations. Equilibrium, then there must be relationship between strain and displacement, and third one is the material law, that is stress and strain must be related by some. So, here if it is a stress and strain, so we know that yes, that there is only one. So, if you do Hooke's law, so this one will be equal to some E times strain. So, this completes the basic equations that govern the behavior of a rod, and of course, you have to solve this subject to boundary condition. Boundary condition always comes, equations, these are individual. So, now how to derive one, because now we have got three equations which govern equilibrium, strain, displacement, constitutive. We want to get one equation. So, here we get here from 2 and 3, and remember elasticity problem also is a boundary value problem. So, whatever we have done here, because these equations will give you some kind of, we will just now see what is the kind of equation that it is giving me. It will be second order equation. Second order means it will need integration, will need two constants of integration, that means two boundary points. So, it will be a boundary value problem. Elasticity problem in it is a, it has to be solved as a BVP, boundary value problem. So, it is not something else that you are solving, it is boundary value problem. So, stress equal to, so I can also have, I can combine this E times strain is given from here du by dx. So, I can write stress in terms of displacement by this. Now, if I substitute this over there here, stress value over here in the first one. So, I get d upon dx of sigma x. Sigma x is E times du by dx plus Bx equal to 0. So, I have made use of all the three. I have substituted this into 2, then I have substituted 2, I have substituted 2 into 3, then I have substituted the value of sigma x over here. Now, I have made use of everything and I have got my equation now. If E is constant, if E is not constant, then it will remain just like this. We are always used to equations when all these material constants and things do not, but actually the basic equation is this. E can be a variable, because then it will be changed with respect to x is there. E can change, then it has to be within bracket, but if E is constant, so we can take, if E is constant, then you get here E times second d plus Bx equal to 0. So, I have just given you, now this is a single equation which has come out of these three equations in terms of only, here the variable is only displacement. In terms of displacement, I have got a second order equation. So, it resembles something of your equation that we have been discussing, is it not? This can come down and E is like constant k, and then this is like your P minus P or something, So, otherwise the form is same. Now, Bx in a rod, so physics is important, do not solve only mathematical problem. See, whenever you solve a mathematical problem, always dissect it, understand the physics. What are you solving? What is the problem? So, see, if it is a rod, for example, if I have a rod which is like this, and I have a, I have load which is wiring along this. Normally, we apply a load, which is a function of x. It is a continuous function of x. It can be anything, it can vary, it can be a constant, it can be linear. So, let us assume that this P is this one is the force, applied force per unit length. So, this is per unit length. So, how to relate B? B over here is per unit volume. This is normally we take in our problem as per unit load applied along the length of the rod per unit length. We always say this, So, then how to we have to relate the two. And that is B will be equal to what? So, B so can you relate P with B? B will be equals to
P will be equals to BDA.
No, if you want to convert this P into per unit volume, so P upon A, area of the cross section, will give me length. It will become, because this is per unit length only. If you so length is already included here. If I divide, so this becomes per unit volume. This becomes per unit volume, and that you equate to Bx, which is already. So, this should not be, do not do the other way, per unit volume. So, therefore, you get here E times d square u, people come with plus P over A equal to 0. Therefore, our equation comes out to be, which is a well known equation, but not many people know. These are not derived. I do not know any book derives this. They give you directly. The equation governing the behavior of a rod is given by this equation, which looks similar to your flexure formula, except that this is second order, flexure is fourth order, and it is P by E I. Instead of E A, it is E I. P by, and P is the transverse load there, not axial load. In a beam, because you want bending, flexure. So, this is what is your governing equation. So, this is the governing equation. So, this is very much similar to whatever we have as quasi harmonic problem that we have already. So, what I want to say that this problem is similar to whatever we have already done, except that it will require some simple. So, yeah, that will be dealt with separately. Axial load, concentrated load, that will go directly to the, you see, we in FEM any distributed force is converted into nodal or nodal forces, because nodes are my key points. If there is a nodal force, that will directly go to the node.
And Bx will be 0.
Bx does not come there, yes. Bx is always for distributed. So, what is the, can somebody tell me what will be the, supposing we have this problem. So, what will be our, now if I have a rod element, now again rod, although area of cross section is shown, it is a line element, it is only a line. So, we have two, let us say a rod defined by two extremities which we call node, and this is let us say total domain, does not matter. We have some P 1, let us say, I am not saying, so node 1, node 2, and let us again say that the displacements of these nodes are u 1 and u 2. In any, this is my total length and which you are calling as element. So, in FEM what we do is we relate this, we relate P 1, P 2 nodal forces at the nodes to the nodal displacements at the same nodes. We relate always. See, there is nothing distributed here. So, this distributed problem has to be transformed into a discrete problem which will be given by this. Discrete problem, there is no distribution, everything is concentrated only at the nodes. Now, there is a force at P 1, force at node 2, displacement, displacement. Of course, this has u is a function of x, there is a displacement here. U is in the within the, yes, u is. Now, you must have done, if it, so one is there, if you have a rod, apply two forces. So, we also know how to develop its force displacement relations. For example, how to develop its force displacement relation, we learn from structural analysis that yes, this is a very simple, it has got 2 degree of freedom. So, I can relate these two forces to two displacement by making, by setting one displacement 0 at a time. So, let me set displacement. So, I have a simple problem in which I set 2, fix it 2, only apply at 1. Let me apply here a force. I will not say P 1 because now the problem has changed. P 1, P 2 are the forces acting at the nodes when both the displacements are active. Now, one displacement is non-active, u 2 has become 0. So, let us say that there is a force now required, a P 1 dash is required to produce here unit displacement. That is what is called stiffness. Force required to produce unit displacement. Sorry, force required to produce unit displacement is stiffness of the yes. So P 1 dash force required such that okay. So, P 1 dash will be then equal to k. Huh?
Yes, sir.
That will be k, and then, but then this is not the my idea is something different. Huh? So, that is if it is so, then this is, and k is because it is a displacement. So, we know that k is given by displacement is we have this formula by A delta of any change in length of any actually loaded rod is given by this. So, therefore, there is a P and delta can be related, it will be A by L into delta. If there is a single displacement, P delta is related by this A by L. So, if delta equal to if delta is equal to 1, P becomes itself equal to A by L, which we call as the stiffness of the member, force required to. So, here U1, U2, I want to do superposition.
Yes, sir.
I want to do superposition. So, 1 by 1 U1 displacement, no. So,
2 by 2 matrix.
yes. So, how you help me, because most of you must have done it. I am also very confident, but then I am just so this is so let us say that now P I can write one now P dash P1 dash is not the force for required to produce unit displacement. Let us say here it is very clear, the stiffness of this rod is this A by L. So, let us say I apply P1 dash, I apply such that the displacement here is U1. Then can I now write? Then can I write this P1 dash will be equal to k times U1, and k is A by L into U1. Then we also have, see, for this rod, if you apply equilibrium P1 dash, now here I am drawing the free body diagram. I am drawing the free, I have removed the support, free body diagram. So, there must be a reaction. Let me call this reaction as direction I am keeping the same. Let me call this as P2 dash, this reaction. So, I get here, this is the equilibrium free body diagram of the rod. So, I get here P1 dash plus P2 dash should be 0. Therefore, P2 dash is equal to minus A by L into U1. But this is only part of the solution. This is only if one of the degrees of freedom is active. Now, if you do the same thing for the second degree of freedom, that is, fix this U1 equal to 0, apply a P2 double dash such that displacement here is U 2, then we have a relation P 2 equal to A by L. This is U 2. Again draw the free body diagram. For this free body diagram, so here it is. Now, when we draw free body diagram, we need not worry about displacement. It is only forces. So, at this you cut it and show as if the reaction also is in the same direction. So, here we get that this P 1 double dash plus P 2 double dash equal to 0, and therefore, I get here P 1 double dash equal to minus A by L U 2. So, for this, by setting 1 degree of freedom, I have got these relations, but then U 1 U 2 are the. So, if I superpose these two solutions, if I two independent solutions, now, because this one is having only U 1 first one, other one is having U 2 displacement. So, if I superpose, I will have both the displacements. So, therefore, that will represent my this diagram, and therefore, I will have P 1 is equal to P 1 dash plus P 1. I hope I have made it clear. P 1 double dash. Now, this much breakage I do not think it is given in any book, because I was also thinking for some time how to explain, then it comes do not remember everything all the time. So, that is how I got here when I said in the beginning the P 1 unit displacement, but then I got that is and then P 2 equal to P 2 dash plus P 2 double dash. Is it not? This is okay. So, if you put it, you get it here P 1 dash. P 1 dash is what is P 1 dash and what is P 2 dash? Yes, P 1 dash is A by L, U 1, P 1 double dash minus A by L U 2, here P 2 dash minus A by L U 1 and P 2 double dash plus A by L U 2. So, I can combine the two. And then I can write it, this is equal to A by L minus A by L U 1 U 2. Similarly, this also I can combine, P 2 equal to minus A by L A by L. This is very elementary, but elementary things are difficult to explain. Complicated mathematics we can write. Okay. So, P 2 P 1 is this, and this can be combined into again 1. P 1 is this, P 2 is this. So, you can write this in matrix form, and we get here P 1 P 2 equal to A by L minus A by L minus A by L A by L U1, and this we call as K of the member or element, whatever you want to call it, because this relates all the generalized displacement to the generalized forces acting on the nodes, and whatever is in between is called stiffness property, and this has a physical meaning. This is stiffness. That is why we are used to stiffness, that this is a stiffness matrix, while in a thermal problem this was not a stiffness. But we know in structures, yes, this represents stiffness property of the system, and this is all our forces produced by unit displacements. So, stiffness matrix of a simple rod is given by this. The method that we have adopted here to derive this, we did not use any mathematics. We used the governing equations of elasticity, derived the equations, but we did not use the second order equation here, whatever I have derived. Here I have taken only the equilibrium of a rod directly, and so I did not use any minimum principle or minimization of error or weighted residual. So, this approach is called direct approach. So, we have obtained stiffness property of the member K by direct approach. Now, this can be done only for simple problems like this one dimensional rod, one dimensional beam, maybe even 3 dimensional beam, with 6 degrees of freedom, that way it can be done. But the moment it becomes more complex, 2 dimensional problem, it becomes difficult, any 2D. So, in 2D you have to have one of those indirect approaches, and one of the indirect approaches is minimization or weighted residual method. There is another approach for structure analysis only, and that is called no, minimum potential energy, minimum energy approach. See, for equilibrium of any structural system, potential energy must be minimum. So, minimum P E, we can use minimum P, but then that is applied only for structures, not for thermal problem or flow problem or any other. But for flow etc., you have that weighted residual, that will always apply. So, here there was no need for knowing your, but then, so this is direct approach. So, direct approach is used for simple structural systems, especially one dimensional, and we have got this. So, now you have got this. Now, I will not derive for this, because this equation I have already derived. You know how to use weighted residual method to derive the stiffness, that also will give you the same, it will come out to be the same thing. If you use the weighted residual here, you will get the same result that we have obtained here. Okay. So, for this problem we have now learnt that yes, there is a direct approach also, and there is a weighted residual approach, and third approach is minimum potential energy principle. So, that I think I will not is not necessary in this course, or let me see whether. Okay, so this is because basically I want to show you the basic concepts. So, this is the stiffness property of the. So, now if I have a rod, now if I want to solve a problem of rod rod is having different areas of cross section and this lengths are different. Areas of cross sections are different, A1, A2, A3. Modulus of velocities also are different, E1, E2, E3 of these three, and this is one rod. It is not easy to solve by any other method, whatever you have learned, but yes, this discrete method will give us a straightforward solution. Now, this let us say this is clamped here or this is fixed here to the boundary condition we are giving, and let us say that there is let this be free, it does not matter. Let this be at this there is a load yes x1, then there is some distributed load here along this. This is a distributed load P naught. P naught means constant distributed load, while this one there is a distributed load in the central one which is not constant, but it is linear variation. So, here if you see it varies like this. P naught here is starting from here 0, but here it changes to P naught and then it remains constant. There is no distributed load in this element. So, I think we have introduced all the generalities. Now, we want to solve this problem. Yes, under the action of everything is axial, under the action of this it will undergo some compression and stress and strain. So, please find out everything. So, how to do it?
We call it linear distributed force or load.
Which one? This one? Huh?
Use word load or force. Load.
Linearly distributed force per unit length. This is again is per unit length. Dimension of this is per unit length. Okay. P naught. This P naught also is per unit length, but this is constant. This is here. Here P naught is like this. Variation is P naught in this portion. P naught is like this. There is no change. Load is okay. Anyway, I don't think so. Any load is so. So, this is now. So, it is very simple. You see, for each now the basic problem that is coming here is we want to discuss. So, this can be thought of as an assemblage of 3 elements 1, 2, 3 and 4. There are 4 nodes and 3 nodes. We have taken especially this because in each one of these 1 and 2 everything is constant. So, we have taken only 1. Here there is no problem of that is because this stiffness that we have got for this member is not only constant, it does not vary, it is a constant for the element, but it is exact. For the behavior there is no approximation here. This is exact relationship between the nodal force and nodal displacement, which you will not get normally. In a real, there is always phi hat you put approximation, So, you will always have some approximation. Here it is the exact. So, there is no this error in computation of element properties for this problem. Now, basic thing is that I have to transform this triangular load and this distributed load and this distributed load into nodal forces, equivalent nodal forces. So, I will do that first. I will do that first, so that it becomes, I think some of you are also having problem. See, this element has no. So, if this is element number 1, this is element number 2 and this is element number 3. So, for element number 1, there is no distributed force, it is clear. Element number 2, the distributed force is there. I want to transform this into equivalent nodal forces. So, this is P naught per unit length. So, the load I think if you remember whatever we have derived, what is our P 1 and P 2? Because we want to convert this into P 1 and equivalent nodal forces. This distributed force has to be converted into P 1 and P 2. So, what is P 1 and P 2 given by? Yes, very good. Okay. So, we also write it, if you take P, if you combine these P 1 and P 2 into vector P, we also give that as Ni है ना, Ni transpose P dx. We can also write a general formula, instead of Ni Nj, I can write is N transpose. You have to define what is your N. Shape function matrix. What is the shape function matrix here for this? Yes. So, shape function matrix, your shape function matrix for this element is, if there is no problem, you see, I can do everything the way I am doing, So, it is 1 minus, because I have to, this is L2, because this length is L2, 1 minus x L2 and then x by L2. This is my shape function, because this multiplied by u1 and u2 gives you u. This multiplied by u1, this multiplied by u2 is n1, because this is n1 and this is n2. So, this is nothing but n1 and this is n2. So, n1 multiplied by u1 and n2 multiplied by u2 gives you the displacement at any point u. So, that also should be kept in mind.
It is exact, sir. Relation is exact. This relation with u and the shape function is exact now.
Here u linear, you are talking of okay, just let me just think a bit. This u displacement at any point within the element u, which is a function of x, u. This one is u1, this is u2, nodal values. So, this is, we write always n u1 plus n 2, and now he has asked a very pertinent question, that is it a, because actually this is the approximation relation, this is from where finite element starts. Now, here yes, whether this is exact relation or u, it is exact provided provided the displacement within the element varies linearly. Yes, provided displacement within the element varies linearly, and it so happens that in a rod this one, this where whichever we have done rod, when the loads are applied at the nodes, it does vary linearly, that we can. Okay. So, we have to see what is it. So, provided it varies linearly.
Even if it is not varying linearly, then also it should be exact.
Why should it be exact? No, it cannot be exact.
Even in the nodal parameter.
Huh?
Even in the nodal value. So let it vary non-linear also.
No. Then this relationship itself is wrong. Then, if it varies non-linearly, no.
They have got second order differential equation,
Yes.
and the exact solution will be non-linear.
Huh?
Relationship is talking exact solution
Huh.
will be non-linear. Second order differential equation. We can also take quadratic element for this, sir.
You can take.
Then it will be different.
No, you can take quadratic element, but quadratic element may not see this problem is. Immediately I think I will not be able to say anything very clearly, but then it all depends upon load. You see, load will define whether the problem will change from linear to non-linear. See, load is the deciding factor. So, that we have to see, that we have to check. For this one I can say very clearly this will be linear, the first element, there is no, but for these two, for this also constant, yes, this will be linear, but not, here I will have to check. Okay. So,
It's not that because displacement we don't know and we are just approximating by use hat, so it has to be an approximation.
not always. That is why we got exact solution last time, when we solved our problem, and I told you, because exact solution also was linear, and we got our exact, we got 1/2, between 0 and 1, we solved one problem, boundary value problem, and all the nodal values came out to be exact. The reason was because exact solution also was linear, but here it will depend upon the loading. So, please check up. Go to your book on structure analysis, see the solution. Yes, if a rod is subjected to this kind of load, what is the displacement u? U is, what is its, you please check, because I will not be able to say immediately. You please see, and then you will get the answer. So, this is, so okay. So, what I was explaining, that this is the shape function matrix, it is called. We always define horizontal as shape function matrix, not vertical, because this will be horizontal and then u1, u2 will be vertical. So, this is, we have got this. So, we also write like this, and n transpose, and if you can, so then this can be written as in a vertical n transpose, because n is this. So, it is 1 minus x by L2 here, and x by L2 times p Now, P here is linear. Now, what is this? P, now let us say at a distance x, what is the value? It is at a distance x equal to x by L2 into P naught. It is x by L2 into, is it not? This value is times the value at any distance x from the left end is how much? X, when x equal to 0, it is this, when x is equal to P naught. Yes, x by L2 into P naught. So, this is P is equal to P naught x by L2 dx. This can be integrated from 0 to L2 and you will get for element number 2, if you can integrate this, both these, because this is, yes, see you have this becomes quadratic function here, here also quadratic function 0 to L2. So, please integrate this and you will get your values. Ultimately, it should come out to be, I can only tell you, it will be 1/3, 2/3, because it is a triangular loading. Na? So, it will come out to be P naught L, total load is how much? Total load is P naught into L2 by 2. So, 1/3 of P naught L2 by 2, because this is the total area. Total load acting on the element is P naught into L2 by 2. 1/3 at this node, it should come, you please check, and 2/3 P naught L2 by, I am giving you a, so please check. Okay. So, I think we stop here because next class will be there.